Presented by Caltech.
Life, should it have originated on Mars, did not have very long to evolve. And so what we're going to do is investigate these ancient rocks to see if life existed in them. The role of a project scientist is to ensure the scientific success of the mission. That's the definition of what a project scientist does. And over the course of the last 7 years, I've worked in the design of the rover, making sure that the engineers who are building the rover actually understand what science needs to address the question of whether life ever existed on Mars. The science team is mostly made up of planetary scientists. We don't often look at rocks that have this primitive form of life in them. And that's because very little of the rock record from that time period is left, so you have to look in the few places on Earth where it's preserved. So we went down to Australia, drove out to this locality, and studied these rocks. And it was very impressive. After a few minutes of looking at it, I got it. I could say, yes, I believe this is evidence of life. It's the kind of thing that would really be exciting if we found it. Pretty much everything around us on Earth is covered with an organic film. Well, we didn't want to send such a film to Mars because we wanted to see whether Mars had its own organics. And when we first started this project 7 or 8 years ago, the science community was adamant. It had to be this clean, it had to be this clean, it had to be this clean. So these surfaces were cleaned to an extraordinary level. And then it turns out that these materials, when they were ultra clean, these metals, no longer slid easily past each other. And that was especially problematic because if we're, say, inserting a tube into the sheath where it's stored and it gets stuck, there's no technician to go and take it out. So we had to change course, and so many people said, you're not going to be able to do that. The engineering team rose to the challenge, and Perseverance became absolutely the right answer for the name, and it also became a kind of a symbolic thing for more than just what we were doing. Just the country isn't entirely shut down. We are persevering. We are still doing great things. If we go there and we find life, that's fantastic. If we go there and don't find life, that's important too. That's at least telling us that life doesn't always occur in a place where conditions are appropriate for it. The message that I give to the science team is the engineering side has built the rover to have all the capabilities that we asked for, has all the instruments that we asked for, has all the sample tubes we asked for. They are all ultra clean, and now it's up to us. Welcome to tonight's Watson Lecture. I'm Ken Farley. I'm a professor of geochemistry at Caltech, and I'm also the project scientist for the Mars 2020 mission. And it's a real pleasure for me to tell you about Perseverance safely on Mars. So we have now been on the surface of Mars for about 20 sols. That's a Martian day. And I want to tell you a little bit about how we got there, talking about entry, descent, and landing, which many of you probably experienced a few weeks ago by tuning in when it was happening. I want to tell you about what the purpose of the mission is, what we're trying to accomplish. And I want to tell you what we will be doing over the years ahead. And for this hometown audience, I also want to tell you a little bit about what this has been like for me personally to participate in this really exciting operation. I want to start with this image here. This is a real image. I will try to tell you the difference when I'm showing you a real image as opposed to an animation or an artist's conception. This is a real image of the most exciting moment of entry, descent, and landing. This is the Perseverance rover touching down on the surface of Mars. This is part of a series of videos, which I'll tell you more about. You might have seen some of, but I want to tell you what this was like when this image came into the operations center. This image came in very late in the evening after landing, might have been sometime around 11 or midnight after a very long day. And there were a few dozen engineers at their consoles up at JPL when this image appeared. It was a bit of a surprise. We didn't really know exactly when this would come in. And it was just jaw-dropping. We had lived through the experience of EDL, and now we got to see it. And so this was just a really fabulous moment to see us arriving. So let me begin by telling you more about entry, descent, and landing. And I just want to review quickly what has to happen during entry, descent, and landing. The rover, all packaged up inside the shell, the spacecraft traveling through space, arrives at Mars at about 12,000 miles per hour. And over the course of a few minutes, it must slow everything down so that the rover can be placed essentially no velocity by itself on the surface. And I'm not going to go through all these various phases that you can see, but it involves aerobraking, parachute, and then what we call powered descent. And in the video I'm going to show you in just a minute, you will see images that were taken from cameras that were mounted on the different spacecraft components to allow different perspectives on entry, descent, and landing. And it is synchronized with the callouts from the operations center at JPL. And I just want to make sure everybody realizes that in real life, these events were not synchronized. The light time between Earth and Mars is about 12 minutes. So the callouts you hear are actually occurring 12 minutes after the events that are captured in the video. And this is one of the great kind of paradoxes of when you're watching the team during EDL, the engineers sitting at their consoles cheering or clapping and or looking concerned, there's nothing they can do. Whatever is going to have happened has already happened. They're just spectators. It's kind of a weird aspect to it. And I want to just sort of convey my own experience with this. You will hear in the videos, you will hear people's voices cracking with emotion because this really was the highest danger moment for this very large mission. And a significant fraction of missions that have gone to Mars have failed. So this was really a moment when this mission was either going to make it or break it. And my experience with this was really, I found it really interesting that literally for weeks before this, I'd wake up in the middle of the night and suddenly start worrying about this, just getting concerned, like, what if we don't land successfully? What if we don't land successfully? And then the night before landing, something happened and I just realized nothing I can do about it. And this team has done everything that can possibly be done. And I didn't feel that nervous through the whole thing. It was great that it wound up well. But at least at the time that landing came, I was confident. It's kind of like when you're on an airplane that has to land in a storm, there's somebody up front that is going to get you there. The engineers have done their job and I trust them. So I'll show you that video, but before we do that, I want to familiarize you a little bit with the area of the landing site. This is in Jezero Crater, and I'm going to go through all of this in some detail in a minute, but you're going to see this landscape in the EDL videos. This area is about 10 kilometers on a side. It's not a very big area. You could probably hike across it in an afternoon. The several features that I want you to look for, both in the EDL video and also in the images that follow, are the delta, the big feature here. I'll tell you how that formed in a little bit. Two craters, one called Hahutsa and one called La Orotava. Those will be quite prominent in the images and in the video. And then this peculiar mitten-shaped feature that is filled with sand dunes and rocky hazards called Seta. So watch out for those during this video. And now I will just run this video of the synchronized callouts from JPL.
We're starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
There's the Delta and Hahutsa.
Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
It's so much bigger than landing Perseverance on Mars. It's about the American spirit, and you brought it back. You brought it back in a moment we so desperately needed.
So here we are. This is a image taken by an orbiter, Mars Reconnaissance orbiter. And the bright square that you see is actually the rover. We can sort of spectacular. We can see the rover sitting on the surface of Mars. And the kind of butterfly wing pattern that you see, that is where the retro rockets blew the dust and sand out of the way, and they left these shallow pits around us. And I just want to point out two things. The rover is sitting between that area, that area called Seta, and you can see all those sand dunes. We could not land successfully there. We would either have difficulty righting the rover if we land in a dune, or possibly driving out. And over this way, I'm going to show you some images in a minute to show you there are lots of boulders over there. And we landed in a little region between those two that we selected during EDL, on board. The rover, the spacecraft on its way down, decided that this was the safest place to land, and it wound up landing very close to where we asked it to go. And that's pretty spectacular that we can arrive within a few meters of where we want to go after traveling literally hundreds of millions of miles to get there. This landing site we've named after Octavia Butler, the science fiction author, and also coincidentally a Pasadena native. Before I tell you more about the mission, I want to acknowledge something that is really very important. And I think maybe we lose sight of it a lot when we talk about a robot exploring space. It is still about people. This is the last picture that we took of the Mars 2020 team up at JPL. You can see this was pre-COVID. If only we could still gather like this. But I want to acknowledge that it is a group of this size that allows something like this to happen. And what I'm going to tell you about is the Mars 2020 mission, and also about a series of follow-on missions that in many ways I kind of feel are like a relay race. And in the first segment of the relay race, the team of people that you see here, as well as other people at JPL and elsewhere, got the rover built, got the spacecraft built, and got it to Mars. That's the first leg. They have now successfully gotten us to Mars, and they are handing it off to the science team, as well as a group of engineers that are absolutely essential to keep the rover going. And then we are going to hand off the samples that we collect to another set of missions that will bring them back to Earth. And so this is really an intergenerational effort. It is, I would suspect, amongst the largest scientific endeavors ever undertaken. And so from that point of view, it is important to realize that there are lots of people, and many of these people may be your friends and neighbors here locally. And I also want to comment on what President Biden said at the end of that clip. This mission was in the home stretch when the curtain came down because of COVID. There were many challenges for us to get the spacecraft to launch and to figure out how to operate it in the COVID world. You might have noticed in the Mission Operations Center during landing, there were relatively few people in there. We had to figure out how to make that work. And the idea that somehow Perseverance was symbolic for the country, we felt that. We felt like, this is something that we have to do. We have to make it work. So it is truly spectacular that we have succeeded in getting to where we are. Okay, so let me tell you a little bit about the rover. This rover is very similar to Curiosity, if you're familiar with it. It's about the size of a car. It has 7 science instruments distributed around on it. And for this talk, I'm not going to tell you about what each of the instruments does in favor of actually showing you some of the results that we have. But I do want to tell you that the 3 major goals of the mission are, first, to seek evidence of ancient life on Mars. And I'll explain that, some of the qualifiers that are in there, why they're in there. We are going to prepare samples to bring back to Earth. We, the Mars 2020 team, are not going to bring them back. Perseverance will remain forever on Mars, but a future mission could bring them back. And it's important to understand why these 2 goals are linked. The idea of finding life on another planet has an enormous burden of proof. And the likelihood that any instrument that we can presently fly could detect life in a way that was sufficiently compelling to overcome that burden, that likelihood is small. And so this is a good reason to bring samples back where you can use the full arsenal of terrestrial labs to investigate them, both for things you want to look for, and for things that only occur to you later, like, oh yeah, we should look for this or that or the other thing. So this is how those two goals are linked. And then we also have a third goal, which is to enable the future. And this means to demonstrate technologies that will be useful for future explorers at Mars, possibly even human explorers, to allow their missions to move more swiftly. So first, let me tell you just a little bit about this life goal. The Mars 2020 mission is not tasked with looking for extant life, things that are alive today. And there's a simple reason for that. The present surface of Mars is too cold and too dry, and there's too much radiation to allow any life as we know it to exist on the surface. And that means if you're looking for life, that's not a very good place to look. You could always imagine that there's some kind of life as you don't know it, that's there. But rather than do that, we've taken a different approach, which is that the last, more than a decade, almost 2 decades of exploration of Mars has shown that it was once a very different planet. So this is what Mars looks like today. This is an image from Curiosity. It's a wonderful landscape. It's got lots of interesting geology. But what it doesn't have is anything that looks like water on the surface. But in the distant past, it may have looked something like this. And this image on the right is an artist's conception. It may or may not have looked like this, may or may not have been a northern ocean on the planet. But there is abundant evidence that prior to about 3.6 billion years ago, there was liquid water on the surface. And that tells us, A, it was wetter, B, it was warmer because it was liquid, and C, there must have been an atmosphere because otherwise that water would have just boiled back off. So we know that the surface of Mars was very different in the distant past. And in fact, one of the key discoveries that Curiosity made is there were environments 3.6 billion years ago that are now recorded in the rock record of habitable environments, places where organisms that we know about today on Earth, without having to imagine anything special, where organisms today could have existed. So that's why we are looking for ancient life rather than extant life. What would that life look like? Well, you saw a little bit of that in the introductory clip. You saw our trip to the Pilbara in Western Australia, where we went to look at these rocks. What you're looking at here with a Sharpie for scale is kind of a rock called a stromatolite. And a stromatolite is the equivalent of a fossil, but for microbial life. So this rock was deposited about that same time, about 3.5 billion years ago, and is the oldest uncontested evidence of life on Earth. It was produced when a layer, a film of microbes grew in the mud at the bottom of a lake or a shallow sea. And that layer of organisms, that layer of microbes, actually disrupted the pattern of sediments to produce this kind of bulbous or crinkly structure. And it is widely accepted that no abiogenic process could account for this particular kind of structure. And that's why we see it as evidence of life. So I want to connect the dots here. This rock that you're looking at right now is uncontested evidence of life on Earth 3.5 billion years ago in a shallow lake or sea. We sent Perseverance to a lake that is 3.5 billion years old. So there's a good connection there. And if there was life on one, which there is on Earth, it is not implausible to suggest that it also existed on Mars. Let me also then emphasize that the reason we were looking for microbial life instead of more sophisticated life that might have left, say, bone fossils or tooth fossils or leaf fossils, is that the complexity of life on Earth didn't reach the level of that capability of leaving those kinds of fossils until about 600 million years ago. So there's about a 3 billion year difference between when rocks like the one you see here were deposited and when the first real fossils that you might show to your child and get excited about, till those were left. And so just being explicit here, we are using Earth as an analogy because it's the only analogy we have. We would be definitely excited if we found something that looked like a more sophisticated form of life, but we are realistically looking for microbial life. Okay, so here is one of the really compelling indications that there was once liquid water on Mars. This is a delta, and I'll show you an image of a delta in just a minute. This crater is about 40 kilometers across. It has an inlet canyon that you can see in the crater rim. So that's this back here is the crater rim. Oops, sorry about that. That's the crater rim with the delta. And the red dot that you see there is where we landed. So the importance of this image is simply to drive home the point. We are not really going out on a limb when we say that this crater was filled with a lake. And because there was an outlet channel, we actually know since we know the elevation of the spillover point, we know how deep this lake was. It was hundreds of meters deep. This was a huge lake. So although this image is an artist's conception, we have very strong confidence that this is roughly correct, that there was a river flowing into this lake that was hundreds of meters deep. We don't know how long that environment existed, but it was at least there long enough to deposit that big delta. Just to remind everybody what a delta is and why this is such really incontrovertible evidence, a delta is produced when a river, as you see in this image here, transports sediment until it hits the slack water of a lake or a sea. And without the turbulence of the river, the sediment just falls out and it produces this kind of braided structure that you see in this image here. And one thing, so that provides strong evidence that there was water. But another thing that it does, which is really important, is it is an abode for life. And you can see that from all the different colors on here. I don't know exactly what those are, but those are certainly some form of life that has colonized the muddy surface. So that's great. This is a habitable environment. But what's even better is that mud buries the organisms and preserves them. So we say that this kind of environment has high preservation potential. The rocks are likely to actually record evidence that there had once been life in it, if that were the case. And that's different, for example, than if you went to, say, a Sierra mountain stream that's filled with rocks and boulders. The likelihood that something would get preserved and still look like something that you could recognize is very low. So a delta is really an attractive environment for habitability and for preservation potential. And that was a key reason we decided to go to Jezero Crater. So here we are. I'm going to show you a few images. We've only been on the surface of Mars for 20 sols. That's just about 20 Earth days. And we are mostly checking out the rover. The science mission will begin in earnest probably maybe 4 or 5 weeks from now. We've got a lot to do, and I'll show you what that is. But a lot of it's checkout. And the two images on the left show some of the checkout. You can see us for the very first time wiggling our wheels and rotating the turret. So that's on the robotic arm. That is where several of our really key science instruments are located. And there's also a drill out there, which I'll show you more about in a minute. So we're just spinning it around to make sure everything looks good. And I'm going to show you a video of the turret in action. But one thing to keep in mind is that turret weighs about 45 kilograms. It's almost 100 pounds, and it's perched out on a long arm. It is a very tricky thing to manipulate. So when you see the movie of that being manipulated, just recognize how delicate that whole thing is. The image on the right is one of my favorites. We arrived from space and we just drove away. It's one of the special things about this kind of landing called the sky crane. The rover was left with nothing around it. It's literally like somebody beamed the rover to the surface of the planet, and then we just drove off. So these tracks will be on Mars for many decades to come, recording our arrival from nowhere and driving away. This is about the extent of our drive. We've driven, I think, in total maybe 70 meters so far. But we're just warming up to do some real exploration. This is a wonderfully detailed 360-degree panorama, and you will not be able to appreciate it certainly in this Zoom session, and you would not be able to appreciate it even if you downloaded this image and looked at it on your own computer unless you zoomed in. And you can keep on zooming in and see incredible detail. I strongly encourage you to do this. The Mars 2020 website at JPL, the NASA JPL website, has these images for you to peruse. They're super fun because there's all sorts of interesting things to look at. But I'm gonna show you some of them that caught my attention and has got the science team interested. The two things that you can see pretty prominently in here are the lighter circles that you see right here and right here. Those were things that I called the butterfly wings. That's where the rockets blasted the sand off of the surface. So let me show you some highlighted areas where we've zoomed in, and I can tell you about some of the features we've already been talking about on the science team. Before I show you that, let me show you where I'm going to be directing your attention. The first few images are going to be looking this way. So we landed here, that's Butler Landing, and we're going to be looking off in this direction. And then, so that'd be the first, I think, 2 images. And then I'm going to show you what it looks like in this direction. So this is essentially a pan through a zoomed in part of that mosaic. And I like the panning effect because it gives you the ability to see more than I could just show you in a static image. So there are 3 things that you can see. It just cycled back. The delta. So the very prominent feature here, that's the delta. That's the crater rim. And these sand dunes here are that feature I called Zeta, where if we had landed there, we would not have been successful. So a couple of really interesting things we see already. The first is the delta is capped with hard rock, like right here. This is a very typical feature. You go out in the desert, you see this all over the place. There is a resistant rock layer. We speculate that this is sandstone. It's very typically a resistant layer. The stuff below it is buried, and that is almost certainly softer stuff, maybe mud that was deposited in the lake. We're going to go investigate that. We'll probably be there in maybe a year's time. It's quite a long drive over there. The other interesting thing, which was a surprise, and you'll see it in some of the other images, is there are a lot of boulders here. I think most of us were surprised by the number of boulders that are laying around here. These are smaller than we could have seen with orbital imagery. And it is a first order question. If you are out in the middle of a lake, where did the boulders come from? It is not what you expect. You need some sort of mechanism to transport those boulders or make them in place. So we're investigating that now, which is puzzling over how that actually happened. And the other thing, I'll wait for this to cycle back, thing that excited me a lot when I first saw it is that image there. That's the inlet channel right here. So this was super exciting to me to say, wow, we are sitting in the bottom of this place that we have been studying for so long. There's the inlet canyon. This is the real deal. Really exciting. So here we have a zoomed in look at one of the pieces of the delta. This is one that we assign names to things to make it easier to talk about them. We call this one Kodiak. It's a really prominent feature that I hope we explore in the not too distant future. And in the foreground, you see meter scale boulders, as I was referring to. And you can see why it was okay where we landed, because in the foreground, so this is probably 60 or 70 meters away. In the foreground here, there's almost nothing. And that's why this was a safe place to land. We knew from orbit, at least at that level, that it was a pretty safe place to land. And then looking off in the other direction, I had at one point early on, I said, look at the crater called La Orotava. And what you see scrolling right into the middle now is this much smaller impact crater right here. You can see the crater rim of La Orotava, which is a few tens of meters across. And it provides at least some idea of where those boulders might have come from, just small local impacts that have shattered up the rock and deposited them on the surface. But this surface really looks very different than the surface, for example, of Gale Crater, where boulders like this are not that common. There's also some really interesting features off in the distance on the crater rim. Some of those are crater rim features produced by the impact that made the crater, and some of them are actually lake deposit features. So here is a kind of a gallery of rocks that we have seen. A first order question that every geologist, when you put them out in the field, they will ask, what kind of rock is this? Igneous, sedimentary, metamorphic? It is like the first order characterization. It's like when you take your kid out to the park and they pick something up and, they say, Daddy, what is this? The first thing goes through your head is animal, vegetable, or mineral. Well, this is like, what is this rock? And I will tell you, we don't know. It is not obvious to us. The two logical choices are it's a lava flow or it is rock that was deposited in a lake somehow. We are trying to sort that out. But let me show you that there are features, or talk you through some features here that we do think we understand and some that we don't. So in the lower right-hand corner, you see a rock that we affectionately call the harbor seal. It is a kind of a rock called a ventifact, and it is telling us about an important feature of this landscape, and that it has been sculpted by wind blowing sand. So wind picks up sand grains, and anything that is standing proud of the surface gets abraded. And so it produces these very characteristic fluted structures and other kinds of features that we see in many of the images. So wind is important. And then right above that, the rock that looks like it's planed off right at ground level, that is also, because it is planed off at ground level, strongly suggestive of wind erosion. The wind has basically just sanded it down to the point where there's nothing that the wind can do on it anymore. In the lower left is a different kind of a rock. This is one that was exposed by the jets of the rocket. That kind of flaky texture that you see in the upper left, It is a matter of debate how it was produced, but one reasonable interpretation is this is weathering by water. And of course, that is something that you would logically expect in a lake. It is not that common to see this kind of feature on Mars. We're pretty excited about that in addition to wind type processes, we may see in these rocks evidence of water. And then and just let me restate again, but we still don't know whether these are sedimentary, meaning deposited by water or by the wind, or whether they are lava flows. We still want to know that. That'll be hugely important in our thinking. And then the image on the left, I think is sort of a cruel joke. We call these the holy rocks, not very imaginative. But I like to say that you could lock the entire science team in a room and tell them they cannot get out until they all agree on what the origin of those holes is, and we would starve to death. There are lots of different interpretations for what those holes could be, and we just don't know. They're just a fascinating feature. Could be volcanic, those could be gas bubbles, those could be produced by wind erosion or any number of other processes. So they're really interesting, fun to look at, but we don't know what they mean. So that's some of what we've seen so far. We will explore further and we will collect samples. So we are going to collect about 40 samples into tubes that you can see on the left. And you heard me expressing my excitement about them being ultra clean. Well, these are ultra clean tubes, and we will drill into each one of these tubes a core of rock that is about the size and shape of a piece of chalkboard chalk. And then we will seal it up. And we do that using the drill mounted on the robotic arm. So let me show you how that actually is going to go. I'll run this movie of sampling. So we will likely do this not before the summer, because there's a lot of activities here that have to get checked out to make sure they work before we do it. So here we've roved up to a rock that we wish to sample. So now mounted out on that long robotic arm is this 45 kilogram object that needs to be very delicately placed at the surface. Rotary percussive drill, kind of like a hammer drill that you buy at Home Depot, drilling the sample right into that tube, which is inside the bit. And then we ingest it back into the rover to process it. There, that yellow thing is the tube. And now you will see the most complicated robotic system that's ever been flown for planetary exploration. This is an incredible piece of hardware. The little circles that you see, the honeycomb, each one of those is a storage location for a different sample tube. And what you see going on there is what we call sample handling. It's making sure there's sample in there, takes a picture of it, seals the tube. And now we take that tube and we put it back into one of the little compartments where they are stored on the rover until we make a transfer by one means or another to the future missions, which can bring them back to Earth. And I'll show you that in just a second. So that's how sampling is going to work. This was one of the really major new innovations that had to be developed for this rover. That's a very sophisticated piece of hardware. And one example I like to give is, when you want to get your bag of potato chips out of the vending machine and it gets jammed up, you grab the vending machine and shake it a little and hope that it dispenses your chips. Well, there is no way to shake this thing. And so this device not only is very complicated, but it has to be foolproof. There's no technician who's going to go and work on it. So here is what Mars sample return looks like. This is this intergenerational effort that we're on the first step of it, really. It is 3 missions as presently conceived. The Mars 2020 mission collects samples and we transfer them to a follow-on mission that has the Mars Ascent Vehicle, a rocket. And we are presently considering the different ways to do it. This is a joint, right now it's a joint NASA-ESA effort, and JPL is deeply involved in this. There is likely to be a fetch rover with this, what we call the sample return lander, this follow-on mission. And we will, Mars 2020, will put the samples on the ground, and the fetch rover will pick them up and ferry them to the rocket, the Mars Ascent Vehicle, and put them in a container about the size of a soccer ball, we should call the orbiting sample. That's inside the rocket. And that is then launched into orbit. And in the final image on the right, you see the third mission, which will capture this soccer ball from orbit and bring it back to Earth. And the current notion is that the samples could be back to Earth as early as 2031. And when I say that, people often think, oh, gosh, that seems like a long time from now. But I'll just tell you that since I was a graduate student in the 1980s, a Mars sample return was always a decade away. And it's still a decade away, but at least we've started. And I would say for the younger folks in the audience, when these samples come back, they're going to be huge. It is going to be a fantastic opportunity to learn about Mars. And what I find particularly exciting, it's not my field, but I think it's going to be really exciting to see how the science community really grapples with looking for life that isn't us, looking for life as we don't know it. People have thought about that, but some scientist in the future is going to be handed one of these tubes and be told, go figure out whether there's evidence of life in there. Not life as we know it necessarily, possibly life as we don't know it. For the first time, people are really going to have to grapple with that. So I find that really exciting that that's coming soon. We have a prime mission of about 2 years, 2 Earth years, which is equivalent to 1 Mars year. We landed at the red star there, the Butler landing. And that area called Seta that I told you was you don't want to land in, you also don't want to drive on it because you'll get the rover stuck in sand. So we have a first order decision to make in the coming weeks. Do we go clockwise around Seta or we go counterclockwise? So the science team is now trying to figure out what we would see on the different routes and how important they are to fulfilling our goals for the mission. And then we are likely to pick up a route that's kind of like the yellow one, where we go up to the Delta and explore environments of the Delta. And then ultimately we head up to the crater rim. And if we are fortunate enough to have an extended mission, that is what occurs after the prime mission, so more than 2 years from now, we will explore the crater rim and actually drive up that rim, which is about 1,400 meters high, and explore the highlands around the crater. So that's kind of the long view of what this mission is about. And we'll be collecting samples all along the way until we hand them off to the sample return mission. And the final thing I want to show you is the one of the Enable the Future features of the mission. There are really 2 prominent ones which you may have heard about. One of them is an instrument which demonstrates the conversion of atmospheric carbon dioxide to oxygen. This is something that would be very useful for human explorers in the future to not have to bring all of their oxygen with them, but to be able to make it on the surface of the planet. So we have a small scale version of that, which we call MOXIE, and that will likely run within the next few weeks. We will demonstrate that capability. This is a standard thing that NASA does is kind of shake out some of the technical complexities in a relatively low stakes effort. For example, if this instrument called MOXIE does not work, it is not a huge deal for the entire mission. If you were an astronaut counting on that oxygen being there, you might think it was a big deal if it didn't work. We have another similar capability, and that is a helicopter. So I'm going to show you the video of the helicopter in just a second. The helicopter is likely to fly for the first time sometime in the next few weeks. So this is one of the activities that we need to accomplish before we really embark on the science mission on the routes that I show you here. So let me run the helicopter movie. We deploy it from the rover. It's mounted on the bottom of the rover. We deploy it to the ground. Those blades on the helicopter are about 1 meter across because the atmospheric pressure on Mars is only about 1% of the Earth's surface pressure. So it can't be a typical drone that you'd buy in a hobby shop. So there are a series of test flights, 5 test flights that the helicopter will be put through. And they range in complexity from just going up and going down to the example that you see here, where the helicopter flies off, takes some images, and returns to its original landing site, which is a place where we know that it's safe to land. All those boulders that I told you about, those are not a place you want to land a rover or a helicopter. So that's what the helicopter is going to do to demonstrate controlled flight for the first time on another planet. So that'll be super exciting. And that is all I was going to present. I'm happy to answer any questions you might have right now. Thank you for listening.